Okay, here we've got the notes for section 4, which deals with derivatives of exponential and logarithmic functions. So we've got some definitions up here first. The derivative of e to the x. So e to the x is actually unique. The derivative of e to the x is itself. It's also e to the x. Now the second bullet point there gives us the chain rule version of this, essentially, where we don't necessarily have just x in the exponent. So the derivative of e to any power is equal to e to that power times the derivative of that power. So for example 1, find dy dx if y is equal to this. So the rule is, so to take the derivative of an e function, it's the original expression, that's the e to the u part, and then times the derivative of the exponent, which in this case is going to be 1 plus 2x. And that would be your answer. You may sometimes see it written like this, just because you don't normally want to have your exponents right up against stuff, but that's relatively straightforward. All right, so down here, we've got the derivative of a to the x, so a is some number. And here's the derivation for it, but your rule is right here. So the derivative of a to some power, so some number to a power, is equal to the original expression times the natural log of a times the derivative of the exponent. Now that is technically true for e to the x, but the reason that we don't write it out that way is that if these a's all became e's, e to the u, ln, e, du dx, ln e is 1, so it would disappear anyway, so we don't have to worry about it. All right, so example 2 here says at what point on the graph of the function y equals 2 to the t minus 3 does a tangent line have slope 21? So I need this derivative, because that's the same thing as the slope. So the derivative of a to that is going to be the original expression times the natural log of the base, and then times the derivative of the exponent, which happens to just be 1. So technically there's a times 1, but we don't need to show it. The derivative of negative 3 is 0, so it also doesn't appear. So it says have a slope of 21. So I want to know when this is equal to 21. So I need to get the 2 to the t by itself first, so I can do that by dividing by ln 2. Now to get t out of the exponent, I have to take the natural log of both sides. So this becomes ln 2 to the t equals the natural log of 21 over ln 2. Now when you do this, the exponent can be moved out front. So we have this, and then I can divide the ln 2 across. So I get ln natural log of 21 over the natural log of 2 divided by the natural log of 2. And that's all numbers, even though it looks like a hot mess. You can go in my calculator. So 21 divided by the natural log of 2, the natural log of that, divided by the natural log of 2, gives me a t value of about 4.92. So when t is 4.92, the tangent line has a slope of 21. So now we've got the logarithms, so the derivative of the natural log. So the derivative of the natural log is 1 over whatever you're taking the natural log of times the derivative of what you're taking the natural log of. So example 3 says a line with slope m passes to the origin and is tangent to the graph of y equals ln x. What is the value of m? So the trick here is it tells us it passes through the origin, so it has to pass to the point 0, 0. So it's tangent to the graph of y equals ln x. So I need m, which means I need y prime, which is 1 over x. We're going to have a problem here. So let's see here, because the problem is if I put 0 in, so I get undefined. So what is the value of m? Well, there you go. The m is undefined. So this line would have to be vertical. If you look at the graph of ln x, you can kind of see that it falls down. It actually never goes past 0, so the line becomes vertical and it runs essentially right next to the x-axis, or right on top, sorry, of the y-axis. So a vertical line has to have a undefined slope. Okay, that's that. Which brings us to the derivative of log, so where a is some number. So here's our rule. So it's 1 over whatever's inside times the natural log of the base. So this is kind of like the exponential, except we use ln's, or lna shows up in both the exponential form and this. Now note that even though this is a log, this is a natural log, and that's supposed to be true. And then du dx is your derivative of the exponent. So find dy dx if y equals log base a of a to the sine x. Okay. So y equals log base a of a to the sine x. So this is actually going to be a chain rule because I have this stuff inside that. So we start with the outside. So the derivative of this, 1 over u, so a to the sine x, and then ln a, so ln a, because you don't know the value for a, so ln a just stays a, the base is here. Then times the derivative of this, so that's a raised to a power is the original expression times the natural log of the base times the derivative of the exponent, which is just cosine x. And this does look like a very long, messy string, but these guys actually cancel. Those guys actually cancel. So the whole thing just boils down to the cosine of x. And that's actually a very long way to do this problem because the alternate method looks like this. So since I have a logarithm, this exponent can't get moved out front, so it becomes sine x times log base a of a. Now, log is what power of a is equal to a. Well, a is the first power of a, so this just becomes sine x times 1, which is just sine x. And the derivative of sine x is cosine x. Okay, so once again, power rule. We just keep refreshing this, we just keep adding new things. So this is for arbitrary real powers, so it doesn't matter if you don't have a number or anything up there, like the power rule still holds. So this would become y prime, so exponent multiplies out front, and then I subtract 1 from the exponent. But you can't work that out, so it just stays root 2 minus 1. So down here, this guy's technically a chain rule. So the pi comes out front, leave the inside alone, and then you subtract 1 from your exponent, and then you multiply by the derivative of the inside. Well, the derivative of 2 is 0. This guy here, though, is another chain rule. So the derivative of sine 3x is take the derivative of the sine, leave the 3x alone, and then multiply by the derivative of the 3x. So cleaning this up, you would have 3 pi cosine 3x 2 plus sine x to the pi minus 1. And that would be your final solution. Okay, example 6 says if f of x equals ln x minus 3, find f prime of x, state the domain of the derivative. Okay, so we're going to just make this so f prime is the derivative. So the derivative of the natural log is 1 over whatever's inside the log times the derivative of what's inside the log. So this would be just 1 over x minus 3. So the domain of f prime is x cannot equal 3 because that would make this 0. But we also have to look over here. You can't take the natural log of a negative number, so x has to be greater than 3, which this part here, x greater than 3, does cover this part. So the domain is actually just that. So the x not equals 3 comes from the actual equation for the derivative. You can't plug 3 in, you get 0 on the bottom. But the original expression, the natural log of x minus 3, only exists if x is more than 3. Because if x is less than 3 or equal to 3, you get the natural log of 0 or the natural log of a negative number, and those cannot be evaluated. So this is actually the domain, simply because the function doesn't exist left of 3. Okay. So 7 here, we got y equals x to the x, so we got to do a little bit of rearranging first. We can't actually do that derivative because we don't have a formula for variable to a variable power. So we need to fix this first. So I need to get that x out of the exponent, And I do that with a natural log. So if I take the natural log of both sides, that lets me move the power out front. So now I can take derivatives. So over here on the left, derivative of a natural log is 1 over. But that was a y, so I get a y prime. Over here on the right, this is a product rule. It's two things being multiplied together. So the derivative of x is 1. Leave the second part alone, that's v. And then plus, leave u alone, and take the derivative of v. The derivative of the natural log is 1 over. So this becomes 1 over y times y prime equals the natural log of x plus 1. Because x times 1 over x, those x's cancel. So I need to get y prime by itself. So since I'm dividing by y here, if I multiply everybody by y, I get y ln x plus 1. But y is x to the x, so I can rewrite this as x to the x times the natural log of x plus 1. So that's just here replacing what y is actually equal to. So there's y prime in terms of x. Okay, example 8, which I believe is the last, maybe not. Spread of a flu in a certain school is modeled by the equation this 100 over 1 plus e to the 3 minus t, where pt is the total number of students infected t days after the flu was first noticed. Many of them may already be well again at a given later time t. So estimate the initial number of students infected with the flu. So that would happen when initial is when t is 0. So we're doing p of 0 is equal to 100 over 1 plus e to the 3 minus 0, which is 100 over 1 plus e cubed. And that can all just go in my calculator. So 1 plus e cubed and then 100 divided by that gives us about 4.7, so we'll call it 5. So you can't have fractional people. So about 5 people, or sorry, 4.7, which is about 5. How fast is the flu spreading after 3 days? So this is the derivative. We want p prime. So our original expression, so we can do this with everything in, might run out of room, looks like that. So that is a quotient rule. So quotient rule is derivative of the top, which is 0, times the bottom, minus the top, times the derivative of the bottom. So the derivative of the denominator, derivative of 1 is 0, it goes away. The derivative of an e term is the original expression, and then times the derivative of the exponent. So that's where the negative 1 comes from. It's the derivative of the 3 minus t. And that's all over the denominator squared. So let's see if we can do a little bit of cleaning up here. So that part is all 0. 0 times anything goes away. Over here I've got negative 100 times negative 1, so that's just positive 100 times e to the 3 minus t, all over 1 plus e to the 3 minus t. Now those e to the 3 minus t's don't cancel. Now it says after 3 days, so I need p prime of 3. So that means replace all of my t's with 3. So look like that. So this becomes e to the 0th. And on bottom I have 1 plus e to the 0th. Well, anything to the 0th power is 1. So that is 100 over 2, or so 3 days in, the rate of change, the population is growing by 50 new patients every day. When will the flu spread at its maximum rate? What is that rate? Okay, so to do that, I'm actually going to look at the graph. I'm going to take my p prime equation, which is 100 times e to the 3 minus t, all over, oh shoot, that's not the answer, squared, 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 squared. So this should be 4, which means it's 25 people, not 50. I lost my squared from up there. Okay, 1 plus e to the 3 minus t. squared. I'm going to graph this equation. So I've got, to be careful, 100 e to the 3 minus t, except I'm going to use x instead of t, over 1, plus e to the 3 minus t squared. Draw. Now let's see here. Zoom out. Zoom out. So you can see in the graph, I've got kind of a peak. Okay, so now I can see the top of the peak. So on a Casio, to find that maximum value, I can hit G-solve max, and it'll find it for me. So now we actually found it. So when will the flue sped at its maximum rate? So the peak occurs at the point 3, 25. So that is the when. Three days. What is the rate? 25 cases per day. And that, I believe, brings us to the end of the section.